let's go ahead and get started. So welcome everyone to the January meeting for our North Texas AMS chapter. Before I introduce Andrew, first I want to note that our treasurer Stanley's had a few medical issues this past month or so. So we're hoping that he continues his speedy recovery, and hopefully we will see him again here soon. So on that note, I will go ahead and introduce Andrew. Dr. Andrew Rosenow is a research scientist with the University of Oklahoma CIWRO and the National Severe Storms Lab. He has been with OU and NSSL since 2016 as part of their transportation applications team. His work primarily focuses on the detection and prediction of winter weather with an emphasis on heavy snowfall. He also works on the classification of precipitation types and how all of this relates back to transportation needs. Andrew received his bachelor's in meteorology at Valparaiso University and his master's and PhD at the University of Illinois. And he's also a good friend of mine, and I've enjoyed working with him over the years. So the title of his talk is it safe to travel? Which is a really good question. And I will pass it on to Andrew. The floor is yours, sir.
All right, and I've only got one screen, so I cannot see anything from this point forward, but thank you for the introduction. And as Steve mentioned, this talk is going to be all about the question, is it safe to travel? It happens less frequently around here, but today is an excellent example of the type of day where you have a lot of people facing this critical question, and there's not enough decision support out there for the average individual to answer this for themselves. And getting towards a better solution to answering this question has been an area of research that we have ongoing, and I'm going to step briefly into several of the areas that we are exploring to help answer this question. But first, I want to start with the problem itself and the human cost of winter travel. This is something that kind of gets glossed over by a lot of people in terms of how dangerous travel, and especially winter travel, is. And it turns out that winter-related vehicle fatalities outnumber direct fatalities from all other winter hazards. So here's a graph from a paper by Black and Mote in 2015. Looking at how many people died directly due to all of these various weather-related causes, from lightning, tornado, floods, hurricanes, etc. Heat, of course, is the #1 direct killer in terms of weather fatalities. But if I throw on the right-hand side, winter-related motor vehicle, that's 817 fatalities, way off the charts. You combine everything else over this time period, it's 600 for all others combined. Getting adequate information to support travel, and specifically getting it to those that need it, is going to be a whole nother problem that I'm not even going to touch here. This is a big ongoing research effort. So kind of the start on the problem, where do these fatal crashes happen? This is a figure produced by someone that used to be a postdoc here at CIWRO, Dana Tobin. And this is just the gridded location of fatal crashes. And you can see an obvious preference for the kind of the north central to northeast, where you have the combination of winter weather and population density. But they happen all over the country. There's also peaks near cities. The more people there are, the more more opportunities you have to have a fatal winter crash. What are the characteristics of these crashes? This table here is from the CONUS, or by region, all of the fatal crashes involving winter weather. Over the time period of the study, there were about 12,000 fatalities. About 2/3 of them happen on highways. A third of them happen on non-highway roads. And something that might surprise people is that almost 50% of them are single vehicle crashes. That means you think a lot about, oh, I don't trust other drivers, but a lot of the times it's the person behind the wheel that causes the fatal crash. Another about 45% of the time it's two vehicles, and those big pileups you often see in the news are less than 10% in most regions. And we think of trucks as being dangerous. They're about 1/5 of the time involved in these fatal crashes. So you don't want to get involved in a crash with a truck, but usually there's not a truck involved. Conversely, officers say speeding is quite often involved. So watching your speed in these situations is important. But it's also important to think about relative risk. And driving is an inherently dangerous activity. It's actually, at least as of 2018, unintentional injury is the leading cause of death for people from 1 to 44 years of age. I think for certain age brackets that has changed to firearm-related injuries, but it's up there for essentially the entire time period from 1 to the time that our bodies start breaking down. And so what's really important is how does the weather change the risk of driving? There's a background risk of fatalities. And here's a couple of figures, again, that Dana Tobin put together that look at the odds ratio. That is, for these two cases, how does your odds of being involved in a fatal crash change? On the left here, it's just any winter weather versus no adverse weather at all. And you're actually less likely, with the exception of on non-highway roads, you're less likely to be involved in a single vehicle collision. You're more likely to be involved in a double vehicle collision with winter weather. And it's kind of mixed for the bigger pileups, except off of the highways, you tend to have far fewer multiple car pileups. In terms of winter storm warnings versus non-winter storm warnings, you're far less likely to have a traffic fatality in winter weather when you're under a winter storm warning versus a non-winter storm warning. But the bigger events, you're more likely to have a fatality when you are under a winter storm warning. So these are some interesting kind of things to float around as we talk about the weather itself that feeds into these traffic fatalities. They're very complicated in terms of how you get your mind around what the weather we predict eventually leads into the ultimate risk, the ultimate outcomes of these traffic crashes. So what can we do about this? Well, we've been focusing on a major component of the danger, which is answering the following questions. What is going to fall from the sky? How much of it is going to fall? And will it produce ice on the roadways? These three questions together are necessary to then go to the next step for the end traffic engineers and your emergency managers of how safe is it to travel. Answering that question I started the talk off with is it safe to drive? A big piece of that is the road condition, and you need to know all three of these to assess that. And this talk's going to touch on efforts that are underway to address each of these. They're very complicated, so I'm just going to give like a taste of each of them. We'll start with the first question. What is falling? What is coming out of the clouds and is potentially going to accumulate on the ground? So I'm pretty sure everyone here knows what this chart on the right shows, your various precip types and how cold air, warm air distributions play into that. Answering what is going to fall from the sky is a very difficult question, it turns out. It's very sensitive to temperature above the ground, and we rarely measure that. Weather balloons, aircraft soundings, a few other sources that are spatially far apart, and especially in the case of weather balloons, temporally very coarse. You don't get a lot of good quality profiles across the entire country. And yet, if you have the temperature profile wrong, you're in situations where you're close to freezing, you're going to get the precip type wrong. And there's also an observation problem here that ice pellets and sleet in particular, we can't automatically observe. And even with the snow, freezing rain that we can automatically observe, you can get mixes, you can get other things that make automated diagnoses difficult. So the verification data set for whatever you produce to forecast winter precip can have some pretty substantial uncertainty, even if you have perfect input data for your method of determining precip type at the surface. We have developed a number of methods over the years for diagnosing p-type, of varying effectiveness. And one such tool, the one that we're developing here at the lab, is called the spectral bin classifier. And what we've done is we've taken the core of a microphysics scheme and stripped out everything but what's necessary to do precip type. And then we take in a profile, in the sounding example here on the right, and we run it through the SBC and track how particles change from cloud top to the ground. And so we're going to start out here with this yellow line on the sounding. This is the diagnosed cloud top, where the humidity on the sounding says that the cloud is likely that the cloud top for this precipitation event lies. In this case, it's around -5C. So that's actually in the range where we would expect supercooled liquid water. So the algorithm says we start with liquid, even though it's below freezing. This liquid then falls to this layer between the two pink lines here, where it's now above freezing. The algorithm then diagnoses liquid. And then below the bottom pink line, you have the near surface cold layer, which gets beneath the nucleation temperature for liquid. And thus, these liquid drops freeze into ice pellets. And this can be done over with model or observed data. You don't have to have this built into, say, the NWP microphysics scheme. But in addition to just getting the surface p-type out of the algorithm, we can do more. And these additional properties of your p-type diagnosis may be important in answering some of the questions we have going forward. So we can certainly say, is it going to be rain, snow, ice pellets, so sleet, or freezing rain? But because we do these calculations on a per particle basis, rather than just the bulk precipitation type, we can do things like mixes. If the small snowflakes melt, but the large snowflakes don't, you get a rain-snow mix. If the large snowflakes don't melt completely, but the small snowflakes do, and then you go into a cold layer beneath, you can have freezing rain and ice pellets in terms of a mix. You can also discriminate between drizzle or freezing drizzle, which has implications for things like aviation, where the size of the freezing droplet matters, as well as just the amount that's falling. I have an example here of SBC output on the right, and some of you may recognize this date, February 11th, 2021. This is about the time that you had a 130-car pileup in the DFW Metroplex. And the SBC at this point, there's this deep blue next to this red. That says you're in a boundary between larger freezing rain type drops and freezing drizzle, which I think was the report at DFW at the time. So by knowing the properties of the particles, we can say a lot more about the p-type. But there's another discussion that we have to have when we're talking about precipitation type, and it's the probabilistic p-type problem. As a field, we're going from this idea of a single model diagnosis. So run your algorithm for one model output. It gives you an answer, and let's run with it. And we're going to grand ensembles, this idea of the national blend of models. And when we ask the question, what is falling, it's being answered with percentages. There's a 50% probability it's snow. There's a 25% probability it's freezing rain, et cetera, et cetera. And so we're going to have to answer a deterministic type question of how safe are the roads based on inputs that's probabilistic by nature. And there's an even more kind of more basic question that we have to ask, and that's how should we determine probabilities? Should we just pull whatever each model outputs as a p-type? Because at this point, microphysics schemes are becoming more robust, and models are having this built-in answer for p-type. And so I have this plot here on the right, which is a series of forecasts for the Chicago metro area, valid at 6Z on 12 of February 2019. And this is based on work we've done with the HER and looking at different p-type algorithms. And we've been able to identify a problem with this type of, let's just pull it from the model solution. Precipitation type methodologies, how you output precipitation type, have a kind of a character to them. The biases with the algorithm, it likes to output one p-type versus another in certain situations. And this can often overwhelm changes in the temperature fields. So I want you to look at the different p-type analyses. First on the horizontal across a row, these are the same HER forecast hour input. So these are all 6-hour HRRR forecasts. The bottom are 1-hour HRRR forecasts. So on a row, you're using the same thermal information. On a column, you're using the same p-type algorithm. And you'll notice that things look far more similar in the columns, as in using different thermal input, than they do on the rows using different p-type algorithms. And that says a lot about these probabilities, that if you just use one p-type algorithm, you're going to get the character of the p-type algorithm and not necessarily the character of the underlying thermal fields. That's something we are actively working on. But then we get to the next step, and then it's how quickly is whatever is falling accumulating. This is a whole nother area where there's a lot of problems with this. We're not even touching ice pellets because we don't have the observations for it. So I'm going to talk about first ice accretion rate. How quickly does freezing rain accumulate on surfaces? Key idea here is this idea of an ice to liquid ratio, which is the ratio of ice thickness to the depth of liquid that falls. As some of you probably know, freezing rain accumulates ice at different rates depending on several factors, including the temperature. If it's colder, it's easier to freeze. With higher wind speeds, you can take the latent heat of that is released when the ice forms away from the surfaces so that the precipitation that follows can freeze easier. And even the liquid precipitation rate, if it's freezing heavier or if it's raining more heavily, then you aren't going to be able to as efficiently freeze that liquid into ice. And so there's another issue here too of what you're measuring the ice on. I have some figures here from Sanders and Bargenbrook. Look, you have two different ways that you can measure ice accumulations. You can go up to a power line or a tree and determine the radial ice thickness, how thick away from the cylindrical object the ice is, or you have flat ice, which is how on a surface like a sidewalk or a road, how thick the ice forms when the rain can just spread out and form ice. There's a algorithm, a regression model called the freezing rain accumulation model that was presented in this paper that is used operationally to estimate this ice to liquid ratio. But it's typically used in terms of a forecast, usually, just applying it to model data. And one of the things that can do is it can derive both radial and flat ice accumulations. So when we're talking about roads, we're going to obviously be using flat ice, but we also have to keep track of this radial ice, both from a verification perspective, because a lot of reports are going to be people going up to trees or other elevated surfaces and reporting that radial ice, and for a decision support, because obviously power companies and other stakeholders are going to care about that radial ice thickness. So this model at least gives us the ability to provide decision support in both of these ways. What doesn't exist at this point is some kind of national gridded analysis for freezing rain, and that's what we're developing here, something we're calling FRANA, the Freezing Rain Accumulation National Analysis. This is experimental, and we're using the FRAM models as the core for ice liquid ratio and multi-radar, multi-sensor, or MRMS liquid precipitation, also known as QPE, for the amount of liquid that you are freezing with that ILR that comes out of FRAM. And what we're using this for is we're producing gridded accumulations at time frames from an hour to 24 hours. So you can look back like you do here. And over the last day, how much ice is estimated to have frozen across a region. So this is an event from later in December. And you just have this field where you can look at how much ice we've expected on in this case, a radial surface to have accumulated over the time period of interest. And things in this process flow downhill. We use the SVC that I just talked about for precipitation type. And we have done validation of this against ASOS ice accumulations. So we have kind of the statistical backing for this in terms of it works, but we've just deployed this in real time and we're doing our initial testing this winter. And as anyone that's done any kind of R2O can attest to, you start to see problems that you didn't necessarily anticipate when you get into that real-time environment and look at data more closely. It's one I wanted to touch on here is kind of an old foe in radar meteorology, bright banding. This is clearly something we know exists. We've known it exists for a long time. But when you start looking at things in terms of freezing rain, our framework for improving QPE's liquid precipitation in bright bands becomes a problem. We have mitigation measures, but accumulating freezing rain amplifies these errors. Freezing rain events tend to be small liquid equivalent setups. So an error of 25% in a tenth of an inch liquid event is massive in terms of the absolute error in ice accumulations. And what we need to figure out is how do we programmatically separate strong bright banding from thunderstorms, because thunder freezing rain does exist. However, I have an example here from one of the first freezing rain cases we got to look at with Frana that happened here in Oklahoma. And this is just a radar reflectivity scan from Vance Air Force Base. And all of these high reflectivities here are bright banding. You're getting up into the 40s and 50s, and yet we had QPEs that were way too hot for this. We're trying to figure out long-term how to deal with these QPEs alongside Frana. In the short term, we just had to cap Frana. We only allow a certain amount of liquid equivalent to accumulate an hour because this bright banding problem is far more common than the thunder freezing rain problem. The other side of the coin is snow rates, how much snow is falling on the ground, if that's your P-type of the day. And we've gotten a lot of requests from partners of, we need to know snow rate. There's so much decision making that's tied to how quickly snow is accumulating. And forecasters, same thing. We need to know how, for telling our partners what to do, how quickly snow is accumulating. But there's a fundamental problem here. We just do not observe snow rate at adequate spatial or temporal resolutions. Just like with ice, as one of you probably know, there is a snow to liquid ratio, and that is a problem here. I have some extra slides if we have time and there's interest in talking about it, but I'm not going to touch on it in the main meat of this talk for the sake of time. What I'm going to talk about here is looking at ASOS snow intensity. I think everyone here is familiar with what this is. Every single station reports present weather in terms of ASOS sites across the country. And you'll see this used as a stand-in for snow rates in a lot of situations. So you have a snow event down in Dallas, and DFW is reporting moderate snow. And that will just be said as if that tells you how quickly snow is falling. Snow intensity is categorical, light, moderate, and heavy, but it's based on visibility and visibility alone. And this visibility to snow rate relationship is known to be problematic. There's been a lot of works coming out of Rasmussen et al. And some other investigators that says the visibility is not always tied to how much snow is falling. It's a function of other things. The upside of ASOS snow intensity is that you have far better spatial and temporal resolution of observations compared to everything else. And it's like the devil we know. People are used to making decisions based on it. And so what we're trying to do is, can we create an analysis of snow intensity like I just showed you for freezing rain? At the top here, I've just listed off the 3 snow intensity categories. They're just simple relationships between visibility and snow intensity. The ASOS instruments themselves measure extinction. We can calculate visibility based on that with these equations here. The actual numbers there don't matter. Just know that we can go from extinction to visibility. And then work done here at NSSL has developed an expression for extinction based on liquid precipitation rate. So we now have a way to take another parameter that we measure, liquid precipitation rate, QPE, whatever you want to call it, that we produce here at MRMS, and then we can go to extinction and then visibility, and then snow intensity. The only thing that we don't have with this expression, median particle diameter and particle rhyming factor, we may be able to get in the future with radar. Otherwise, we can at least just estimate it. We measure pressure and liquid precipitation rate operationally. And again, with the SBC, I can get in the precipitation type diagnosis and run this expression, run through the data, determine where it's snowing, calculate extinction, go all the way to snow intensity, and create an analysis. So I just want to show what this looks like in practice. This is a case study from 17 February 2022. There was a heavy sudden onset snow event that caused dangerous travel conditions in northern Illinois. This resulted in a 100+ car pileup on I-39 in the afternoon that closed the interstate till the next day. And so on the left here is an example of the snow intensity analysis that we are experimentally able to produce now. In the bottom right is the composite reflectivity analysis. And on the top left figure, I also have orange circles with all ASOS sites that are currently reporting snow at this time. This is a couple hours before the accident or the pileup occurred. And at this time, you have heavy snow being reported across central and western Illinois, lesser snow reported at Davenport, Iowa, and kind of this whole northern part of the shield. You have a lot of sublimation of the snow that's falling, a lot of dry air near the surface, something that's not always going to be visible just looking at a radar reflectivity mosaic, which a lot of people do as just your decision point for driving. I-39, for those of you who are not familiar with this part of the country, is right here. So at this time, a couple hours before before the pileup, we are seeing the southern part of the interstate, heavy snow being diagnosed. Over the northern part of the interstate, you're seeing light to moderate snow being diagnosed. At about the time of the crash, you have now had heavy snow across the entire length of the interstate in Illinois. The crash actually happened, I think, down here. So right on the edge of that transition at 18 UTC, but clearly in the heavy snow part of it by 20 UTC. And again, as you look off in this region here, most of the observations agree. You have some moderate versus heavy, which is just a quarter-mile visibility difference, incidentally. In terms of the ASOS sites, you see a lot more lights up here to the northeast, but again, that's reflective of the dry air sublimating snow, reducing its intensity at most of these sites. Now, question 3, will precipitation freeze or remain frozen? So even if we've answered 1 and 2, we know it's falling, and we know how much of it is falling. What happens when it hits the ground? I'm going to talk a bit about something we've developed here at the lab, ProbSR, Probability Subfreezing Roads. It's a random forest machine learning model. What it predicts is the probability that the road's surface temperature is below freezing. What it doesn't predict is the probability that the road accumulates ice. These are two distinct concepts, and we've had some feedback from forecasters saying, oh, there's snow forming on the road, but ProbSR is saying there's a low probability of sub-freezing roads. These are different concepts, and whether things are on the road is a different question than what this is trying to predict. This algorithm was trained on RWIS data, Road Weather Information System. Here's an example picture of RWIS site here on the right, and uses HER fields as predictors. Here's a list of the predictors. Most of these are fairly self-explanatory, things like temperature, winds, heat fluxes, consecutive hours, how long things have been below or above freezing, sun, dew point, day of the year, what the land use is around the grid point, etc. And just some performance diagrams. If you've never seen these before, don't worry too much about them. Just showing that this algorithm is what we call well-calibrated. That is, when it says there's a 50% chance of the road being sub-freezing, there's about a 50% in verification. There's about 50% of the time that actually happens. And the algorithm also outperforms climatology. That is, it has a higher probability of detection and a lower probability of false detection than climatology. But of course, everything can be improved. And as we've dug into this, we asked the question, how do we make this better? And there's some very interesting things that Mike Baldwin discovered from the analysis that he's done. And that is that ProbSR has a warm bias. Probabilities tend to be too low, below about 2C. So if we look at this field here, this is bias on the y-axis, this her surface temperature on the x-axis, and you're basically unbiased until you hit about 2C, and then the probabilities are too low, a negative bias. And what's also kind of frustrating is in this right figure, you have the error of the algorithm on the y-axis and the surface temperature in the her on the x-axis. Here's the ProbSR algorithm. Here's the climatology, just using the climatological probability of the road being subfreezing. You're always beneath that climo curve, but the points that you are closest to it are right near zero, between -2 and 0C. You always reduce your error, but we would like it to be a little better near zero. And we dug into that, and it turns out that the near zero bias was most present when you had frozen precipitation falling. In the initial training of the model, it didn't turn out that, or it turned out, which was kind of odd, that whether it was precipitating or not didn't really predict the road temperature or the probability of the road being subfreezing very well. But if we go back and just say, is frozen precipitation hitting the ground, that selects out situations where the forecast was highly negatively biased. And this weirdly happened the most, you have the most negative bias around noon, probably when you have this frozen precipitation. It's an extra signal to ignore the incoming solar radiation a little bit more. So a case study to walk you through what this kind of output looks like and what we're able to do with this update. This is a snow event across the Northeast US. There was rain near the coast, snow inland, and the HERB generally captured the P-type transition well. This figure on the right is the fraction of frozen precipitation diagnosed by the HER, and the reflectivity here on the left for reference. And these colors here indicate near 100% frozen precipitation, and all the asterisks are not surprisingly snow from MPing and or ASOS. So this was a case where the HER had the precipitation type right. And if we look at two versions of ProbSR, you have the control on the left, the final version on the right. The colors here are the probability of subfreezing roads. And for the control version, which doesn't have the frozen precip in it, you see low probabilities, blues and maybe greens, in a lot of sites that are black, which are RWIS stations that were below freezing. So sometimes, obviously when you have a 20% probability, it's going to hit 20% of the time, but this seems too low. When we add a predictor for the frozen precipitation hitting the roadway, we increase our probability substantially. And the higher probabilities now encompass the region with a lot of observations of subfreezing road temperatures. And to give an idea where we're heading, now I'm going to show you the snow intensity case study I presented in the second section in ProbSR output from the same time. So if I highlight I-39 here, at this time you had lower snow intensities to the north and higher snow intensities to the south. But at the same time, in the bottom right here, you see probabilities of subfreezing roads were higher to the north and lower to the south. And so this will at least let your DOT partners know in the future, when we can get this stuff together and produce a final product, we expect to be able to tell you whether it's more dangerous to the north, where you have lighter snow on colder roads, or to the south, you have more heavy snow, but warmer road conditions. If we go forward in time to about the time of the crash, ProbSR maximizes across the length of that the I-39. So you're above 50% everywhere. You're probably frozen. Everything that hits the ground is probably not going to melt, but that's of course the fun of probabilities, is you don't know for sure at every pixel. And so this is again a very interesting question of how impactful is that snow going to be when you have a 50-60% probability. Do we need to be messaging that, or do we need a higher probability? These are all questions we like to answer down the line. So kind of some closing thoughts. Again, dangerous winter precipitation that ultimately impacts travelers has multiple components. What's falling? How quickly is it falling? Is it remaining frozen, or is it freezing on the ground? And without good information on all three of these points, you can't answer the ultimate question of, is it safe to travel? And we're working on tools to answer all these questions. Our goal is this one-stop product. Kind of this is the ultimate end of the road for us, is being able to tell you whether the weather that's occurring is sufficient for our downstream partners to diagnose road problems. Think this is cool? You can help. I've shown examples of verification here. A lot of this comes out of MPing. So even if you live somewhat close to an ASOS site, if you see winter precipitation, report it with the MPing app, which is available for your favorite smart device. And something that's I like to highlight, rain reports near freezing are appreciated too. It's very tempting to always report that snow, sleet, freezing rain, but when it's 33 in rain, that's important as well. We need to know when the snow is not making it through. So I'm going to call it a talk here and open for any questions.
Andrew, this is fantastic. Thank you. So yeah, we'll go ahead and open the floor up to questions.
Yeah, I have one. Is there any way to measure road surface temperature so that you can input that as well?
Input that to
your model.
So that's a very interesting question. That ProbSR that I described is it's our way of trying to be able to do that. There are several problems with directly pulling in road surface temperatures. The first is where the data exists in data quality. There's only so many sites across the country. Certain states have a lot of ARWIS stations. Certain states don't have very many, if any. And in the states that do have the sites or the stations, you don't necessarily have that data available to you. A lot of the times there's a difficult dance we have to do with road weather, and that is the road surface conditions are the private sector's job. So if the private sector contractor that runs road weather for a specific state doesn't share the data, we don't have access to it, at least not without a data sharing purchase agreement. And another thing with the road surface is that these ARWIS sites are almost exclusively on highways, busy highways. And right. So if you want to know, and especially in rural areas, what this road surface temperature is, right. There's just no data source for that.
Right.
And so this ProbSR is our attempt to create a gridded field that we can then pull into the whatever model we produce at the end of the day that gets the information about p-type, that gets the information about precip rate, and do that calculation of is this weather impactful? Do we expect whatever's falling to accumulate or not? And we still have to do that dance with, well, we're not necessarily doing road conditions. We're saying this weather is sufficient that you need to worry about you need to tell whoever's doing road conditions for you that, hey, we've got a problem.
Okay, thank you.
There are other questions out there? I'll go ahead and ask one. So a lot of this is, has a dependence on model data. So how challenging is it to work with the different model biases with the output and verification of all of this?
That is a very, very interesting question, and I can't really give you a satisfactory answer. What I can say is that one of the challenges are these model biases, and assessing when, you have algorithmic biases. I talked about that a bit with p-type. When you have a bias in your answer from these tools, is the bias yours? Is the bias the model's? There's some known biases with the HER model. I'm not going to call them out specifically, but we have to figure out when we start doing verification, are we off because of the input? Are we off because of our algorithm? And then there's the problem of verification itself. There's biases in p-type identification. One of the ones that we're pretty sure exists, I don't know if we've been able to explicitly prove it, but is with rain and snow mixes, where, if you imagine you're walking, you're an observer, you're John Q. Public, whoever's looking outside in a situation where you've got this borderline rain-snow mix falling, if you see any snowflake whatsoever, you're going to report rain-snow mix. You're going to M-ping rain-snow mix. But if you see a bunch of snowflakes, a lot of people aren't going to go through the effort to determine, are there raindrops present there as well? That's a much harder question. And so when we tune our algorithms, we're going to have a deficit of these rain-snow mixes where you have 85, 90% snow, a very small amount of liquid. And that in and of itself is going to bias your verification statistics, which is going to bias your algorithm. So it's a complicated problem we are working on. And this doesn't even get into the problem of Rufus and the next generation of NWP, which is supposed to come out next year. And do the changes in Rufus fundamentally change your verification statistics because you are better or worse in certain areas of predicting your thermal fields? Because these thermal fields, and for p-type, for snow intensity, it's going to be things like your dendritic growth zone and saturations. All these fields that come out of the models are going to change in the next year and a half whenever the Rufus rollout happens. And we're going to have all of this work we do to adjust for the biases you're talking about. We're going to have to do that all over again with the new set of model data.
I think that's going to be a fun challenge we're going to have with everything.
Yes.
With winter and severe and rainfall and all the good stuff.
Absolutely.
I guess to follow up with that, so we talked about the models, and there's one other areas of challenges that with radars. And so for this type of work, how big of a challenge is it with radar coverage, both with radar density and the ease of being able to overshoot these features?
It's a big problem in terms of the p-type. If we want to do that discernment between drizzle and rain, you've got to have some way to constrain the problem, be able to tell the algorithm, hey, there's large particles or there's not large particles. Radar is an obvious example of something that can do that. But the biggest or the most common situation where you have freezing drizzle is super shallow liquid clouds. You're talking 1, 2, maybe 3 kilometers deep. And so if you look at a mosaic of reflectivity with freezing drizzle across like the Great Plains, you'll just see these circles around the radar of the small area footprints that the radar is actually capable of detecting where the freezing drizzle is happening. And that's not even getting into the problem of, do we throw it out in QC? Because it's light, it's very similar in character to noise. So that's a problem. Just there's also the problem with what I presented with the snow intensity. If you've got no precip rate, you've got no, you can't calculate extinction. Now with MRMS, we do use the HER model to fill in the gaps in terms of the QPE coverage. So you can use that, but now you're tied to model fields, which the The areas that you have blockage from radars is predominantly the Western US, which is obviously complex terrain. And now you're trying to create an analysis of a field which is predicated on the model getting the complex terrain interactions correct and producing the snow in the right place. So again, it's anything we can do to increase our radar coverage is going to have benefits for all of your end users, and this would be no exception.
Indeed, I appreciate that answer. Are there any other questions out there in the audience? Well, hearing none, I'll ask one last fun one. So, how much work do I have to do to help with this QPE part?
We'll be talking about that soon.
We will be.
It's the biggest problem is there's two problems really. I presented one of them that's kind of a big outstanding issue, that bright banding QPE. And that, I didn't show the output of Frana from the day with that radar reflectivity on purpose because it's so bad. And we've patched together a solution that'll make it more reasonable while we work on the very difficult problem of QPE values that are accurate in that bright banding. The other issue is going to be in terms of snow. Again, it's a light QPE type of phenomenon. And where from the traditional hydrological perspective, you can have, you can say, you know what, I don't have a lot of certainty with these really light echoes in terms of whether it's, 5/100ths an hour versus 3/100ths an hour of liquid equivalent. We'll just bin it to like 1 and 0.01 and 0.05. That small amount of difference in liquid, when you fluff it up at 10-to-1 or more into snow, can start to get to be significant amounts of snow depth. And so that the other piece of it is, even outside of bright band, how can we do better with light liquid that goes into snowfall?
Yeah, there's a lot of challenges to overcome to try and get it right, so that even the little differences in how it's measured, create such a bias. Dale made one comment here. So he wanted to ask, what are the number of MPing reports that you usually see?
That's a great question. And the answer I like to give is a surprisingly high number of reports. MPing at this point is not something that's new. It's not shiny, and we're rolling off of the initial rollout and people getting all excited. This is a decade or more old, if I remember correctly. I think it's hit a decade at this point. And so you would expect for something like this that you would forget, or you would expect with something like this that you would see kind of a roll off of people, and you wouldn't get that continued uptake necessary to get a good data set. And yet, even with events that we look at current year, where we look at the output of our products, as long as it happens during the day, there's usually MPing reports, and especially something through the DFW Metroplex, something through the Northeast part of the US where you have a lot of population density. You get reasonably good coverage. You'll get enough to tell you whether your product is doing well or not in terms of p-type. It's not going to be super precise, but you'll feel confident drawing conclusions from it. Now, at night, there are a few people up at 2 a.m. local time, although I will say if you see a snow event come into Norman, for instance, at 2 a.m, you'll see a nice burst of reports from all the OU college students and the residents of the Weather Center. But as long as you're within the hours that people are usually awake and in a region where there's relatively high population density, you get good numbers of MPing reports. Outside of those, not so much, but there's not a whole lot you can do about that. And there's generally far better coverage of MPing than ASOS or even the AWAS system that the FAA runs.
We appreciate that. So yeah, thank you. And thank you, Dale, for that question. So since we're closing in on the top of the hour, we'll go ahead and start wrapping this up. So Andrew, thank you so much for being our guest speaker this month. And we will work on getting an Amazon gift card to you for, for speaking for us, and whether that will be through the mail or next time I'm in town, which hopefully will be soon. Maybe AMS, who knows? We'll figure it out. Just a quick thing on chapter notes. First, dues. The links are in the emails, and just get them to Stanley if you haven't paid them yet. Next month are the science fairs for both Fort Worth and Dallas. They're great events. They're right in the middle of the month, or more towards middle end of the month. I think they're like that 18th, 19th time frame. We did them last year. It was a lot of fun, a lot of great projects. We appreciate seeing all the work the students are doing. So it's a fun time, and hopefully we can see you all out there. Dave, Greg, I don't know if there's anything you guys wanted to add real quick.
I'll just go ahead, Greg. Age first. Age first. Just remind everybody that there's a website, northtexasams.org. If you need the membership form to pay dues or whatever the Stanley's address is on that form, it's only $10 a year, so no big deal there. And also, there's links to the YouTube site for us where we post these videos on YouTube. So go join and subscribe to that and like the videos, and we'll get wider coverage that way as well.
Appreciate that, Dave. Greg?
Couldn't get the mouse to click on the right button. In regard to the science fairs, I have Fort Worth on the 17th and Dallas on the 18th and 19th. Do we need to start getting folks volunteering to work on that? Because our next meeting is the Tuesday before the Saturday, the first science fair.
Yeah, I believe they start having. I've already started seeing emails for sign-up sheets, and yeah, so I can work on posting that later with the information, and then I guess internally with us officers, we can work on how we want to divvy up the funds for that this year. I know I personally will probably have one challenge with one of the days, just because I will probably have to onboard a new employee, so I will likely have to go to Norman for it, but I will do my best to be there for as much as I can. So thank you, Greg, for that. So I guess that would really be it. So our next meeting is currently scheduled to be Tuesday, 13th of February. It will be located at the North Central Texas Council of Governments at noon, and we'll get you more information for that as we get closer. Other than that, meeting's adjourned. Stay warm. We'll see you next month.